In this video, we're going to use the generic cubic equation of state and derive a cubic polynomial for the compressibility factor z. The compressibility factor is PV over RT, where V is the specific volume. So, with the generic cubic equation of state on the board here that we're starting with, if we want to create this cubic polynomial for the compressibility factor, it would be best for us to start by multiplying each side of the equation by V over RT so that we have Z on one side of the equation. So let's do that. So we have this entire equation here, and if we multiply it by V over RT, these RT's cancel, so we're left with V over V minus B. The next thing we want to do here is get our specific volume V in the denominators so that eventually we can get to a place where we can have common denominators. So to do that, let's divide each numerator and denominator of these two fractions by V and see what we get. So what that would leave us with here, we divide that numerator by V, that's 1, this is 1, and then B over V, minus A on top here. Remember, we're dividing through by V, and then we can divide one of these and there by V. We'll do the one with epsilon times B, so this would become 1 minus epsilon B over V, and then we have the V minus sigma B. The goal of this manipulation is to get a cubic polynomial for the compressibility factor z. And as you can probably guess, the reason I'm messing with the specific volume here on the right-hand side is so that I can write an expression for the right-hand side that has the compressibility factor in it. And the reason why we do this actually is because in many real-world applications, you're going to be given a pressure and a temperature, and you're going to want the specific volume. And with the general cubic equation of state, it's quite difficult to get that volume, but it's much easier to derive this cubic polynomial for the compressibility factor, which is what we're going to do in this video. And then, once you have these critical compressibility factors, the roots of this equation that we'll derive, we know that Z is PV over RT, where V is the specific volume. So you can easily solve for V such that V is ZRT over P. And actually, that's the substitution that we're going to end up making here very soon. There's one thing that I want to point out before we do that. Here, this is the right-hand side of our equation. And what we have is pretty good, because we have our specific volume in the denominator here and in the denominator here, which is good for our substitution. Because, like I said before, eventually we're going to want common denominators. And because we know this specific volume is what we're going to be making a substitution for, we want those to be similar, right? So obviously, if you can see, the problem is with this term here, because we have a specific volume that's not in a denominator at all. But this is actually a pretty easy fix. All we have to do is take it out. So let's actually do that for just this fraction so that we get something that looks like this, where we have epsilon b over the specific volume. I'd like to see the same thing there before we make our substitution. So this is the same over here. A is still up there. So I'm just going to pull the specific volume out here, okay? So we'll have VRT over here, okay? And then this stays the same. And then obviously we didn't change anything, so this still has to be equivalent, which means since we removed the specific volume, this is just a 1. And because this still would have to remain equal to sigma b, it would now be sigma b over v, such that when we multiply in that specific volume, it would be the same as this here. So now we're ready to substitute z into our equation. Now I've given myself some more space on the whiteboard so I can show you how this will work. So hopefully you can see if it's not too blurry, but I have the same equation for z that we had before after we pulled the specific volume out of this term all the way here in the bottom right. So the specific volume is equal to RTZ over P, which is perfect for us because, again, we're going after that common denominator and we want to have z in our right-hand side, and that's exactly what we're going to do. So let's start making that substitution, and you can watch me do this, and hopefully I won't make a mistake. So let's do the first fraction here. So we have 1 over, and then v is there, which means that we are going to flip this fraction, right? So this would be BP, where P is the pressure, over RTZ. Okay? And then A, so once again, this is on the bottom, so we can flip that fraction, so we can put the pressure up here. And then we have RTZ times RT, so we can do R squared T squared Z. Okay? 1 plus epsilon B. And then, same deal again. We'll have the pressure over RTZ. And it will look the same for this, and I'll get down here in a second, that way you can see this. So hopefully all of that's visible. But as you can see, now we have z in both denominators of these fractions, and now it's on our right-hand side. The next thing we want to do here is lump specific terms that we know under one variable and rewrite the equation, basically to simplify what we have. And we want to do this, like I said, with things that we know. So the first thing that really jumps out to me as I look at this from left to right is that this term here has stuff we know. So we have B times P over RTZ. So what do we know? Well, we know P and T. We definitely know R, and B is one of our parameters as well that we know for this substance. So let's rewrite our equation such that a term like beta equals this BP over RT that we know. And this, I think, will be an effective way that we can simplify this cubic polynomial that we're trying to create here. So let's see what we get from that. This would be 1, and we would have beta. Oh, that's a really bad beta. There we go. That's a little better. Beta over z. Okay? And yeah, BP over RT. And as you can see, we have that here as well. We also have AP over R squared T squared as well, which is something that we can also take a look at later. But we have those two as well that we can use for beta. So let's not worry about that for right this second. The reason I mentioned that is obviously A is the other parameter that we'll know. We know the pressure, we know the temperature, we know the ideal gas constant. So we're probably going to have to perform another sort of substitution with a different term, similar to what we've done here with beta. But anyway, we'll worry about that in a second. So this time we would have epsilon beta over z, right? And this would be the same thing except with sigma. So as you can see here, this really works to simplify what we have. Now let's try to represent this AP over R squared T squared Z. So let's see if we can break this up and figure something out. So we have the parameter A times the pressure, ideal gas constant squared, temperature squared, times Z. And let's see, let's kind of try to break this up into stuff that we do actually know. So we have AP over RT, that's pretty simple. Notice that this looks somewhat similar to beta, except we have A instead of B. So that's obviously a good sign. What are we missing here? We still have a 1 over RTZ that would have to be included. Okay. Okay, so one thing that we could do is that, notice that P over RT times B, this would equal beta, right? But if you just had P times RT, then P times RT would equal beta over B. So that's good. Beta term is really, really becoming useful, isn't it? And we have our A term too. So that means we could represent that as A times beta over B. Okay? That's good. What we still have left, now obviously Z is that's the compressibility factor, and we're making a cubic polynomial for the compressibility factor Z. So that is not something we have to be concerned with here. But we do have RT, and let's be honest, like we know that. We know what product that's going to be. So we want to represent that with a variable here. So I would just add it here, keep that in the denominator. And once again, you might ask, oh, where did this RT go, right? And just remember that this here, these three terms came from here, okay? And then all we did is divide both sides by B such that we represent this correctly over here, right, where we have beta and B. So then we have this other RT from the R squared T squared. I just wanted to reiterate that because it can be very, very easy to get lost with all these letters. So this is really good. I don't want to re-represent beta in anything because I already have that term defined for a substitution I performed. But the other things I think are going to be good for us, that we want to represent this as something, right? And obviously don't forget we have our Z over here, which was in the denominator. But again, we'll keep that out of the way. So let's represent this as something, right? So we'll represent that as, I don't know where to put this. We'll do Q equals A over B RT. Okay? All right, and then now let's rewrite this equation and see what it looks like. Now that we have an expression for Q, we can rewrite this equation with Q included. So I made some more space here on the whiteboard, and I have the compressibility factor Z equal to our equation with beta included. And this is what we had from before. So this is the term we're representing, right? This here. And we see that we have A over BRT here in the denominator times beta. And we know that this here is equal to this. So we can represent this as beta times Q, and then we have our Z. Perfect. So what I'm going to do here is put that up here so that I save some space for us, if I can. Which it looks like I'll be able to. So we have Z here on the bottom, and then a beta and Q in the numerator. Now that we've made all the substitutions we can make, I think we're ready to start doing the difficult part of this, which is having common denominators. And there really isn't any shortcut or easy way around this. It's just a lot of grade school algebra skills that, although they're quite simple, they're very easy to make a mistake. So the last thing that I would like to do here, just to clean up our equation for the compressibility factor here, is distribute this Z in here, just to simplify things, because again, we're about to make a common denominator here to get this difference on our right-hand side cleaned up. And to do that, I want to just decrease the amount of factors that I have. So in an effort to try to get that to 2 factors, I'm going to distribute that in. And then to make these factors similar, it would be very beneficial for us to have the whole equation divided by z, because if you notice, if we multiply this in, then we're going to have epsilon beta right there. And it would be really nice to also have the same thing here with just sigma beta, and we can do that by dividing everything by z. And that would also get rid of the z in that little denominator, if you can see it right there. So let's just kind of see where that takes us right before we make these common denominators. So we would have 1 on the left-hand side, obviously. And then when we're dividing, remember that we would be multiplying the denominator by z for each of these fractions, again, because we're multiplying both sides. So this would be z minus beta, and this marker is completely gone. Let me try a different one. Sorry about that. So we would have 1 equals 1 over z minus beta. That's not too bad. Let's distribute that first before I forget and disaster strikes us. So this would become z plus epsilon beta, as I said before. And then, remember, we're dividing, so we multiply in the denominator, so these z's go away, and then that goes on that 1, so it looks just like this. We'd have z plus sigma beta. Okay. So now what we're going to do is we're going to make our common denominator, and we're going to do this just the same way we would do in any algebra class, which is just cross-multiplying. So the common denominator is going to be the product of these 3 terms, okay? And like I said, we're going to be cross-multiplying, and the biggest thing is, obviously, don't forget the negative. So I'm going to write this on the whiteboard for us. As you can see on the board here, I distributed all the terms in the numerator and the denominator, which was quite tedious. But as we can see, because we divided both sides by the compressibility factor before we created our common denominator, we have an excellent situation, because now we can multiply each side by this giant denominator, since all of this is set equal to 1. Then we can subtract each side by the numerator. That way, we have the whole thing set to 0, and then we have some sort of cubic, whoops, not a cubed. We have some sort of cubic polynomial of the compressibility factor, which is exactly what we're trying to do here, and it will be set equal to 0. Now, why is that important? Well, that will be important for us in a future video where we're actually going to use these coefficients and what's known as Cardano's formula to find the roots of our cubic polynomial for the compressibility factor that we attain. And the reason that's important is because once we have z1, z2, z3, v3, I'm jumping ahead of myself there, that's what's going to happen. We are going to be able to get specific volumes from that. And obviously, in reality, there's only going to be 2 volumes when you're below the critical point, and that's going to be the volume of your vapor and the volume of your liquid. The intermediate value, so the one that's in the middle, the lowest one would be your liquid, and then the higher one is going to be your gas, because the gas is less dense. So that seems to obviously make sense with our intuition there. The intermediate volume doesn't actually exist. It's artificial. It's just an artifact of the cubic equation of state. So we won't worry about that when we find those volumes using Python. But for now, what I would like to do here is get our A, B, C, D. And again, those are the coefficients, and they're going to be represented by these letters that are in front of Z. So that's what I'm going to be working on now. Because this equation is so long, I'm actually not going to write out the full expanded version of this cubic polynomial for the compressibility factor that we just found. But obviously in each column here are the different coefficients that would be in front of Z. I included the variable Z, the compressibility factors, just to keep everything straight in my head so that I didn't mess up. The last thing I want to note here, too, before we wrap up this video, is that notice that when I did the numerator, we were subtracting that from both sides. And at the end there, I actually had to change the sign of this because I made a mistake. And I think I had to add a negative sign here, too. But that's just something that's super, super, super important to remember, obviously. But again, basically, to reiterate, you would have the A term in front of the Z cubed, the B term in front of Z squared, and so forth. And then obviously these are going to be extremely useful for us, and we're actually going to be able to find different volumes, specifically the volume that's in a liquid phase and the volume that's in a gaseous state for a single substance when it's below the critical point, which I think is pretty cool. But that will be another video, so I hope this helped you understand why we derive the general cubic equation of state in terms of a cubic polynomial for the compressibility factor and not the specific volume, and how that is actually going to help us find specific volume values, which is really common in real-world applications when we're given pressure and temperature values. So thank you for watching.